Good evening, everyone. Thank you for coming to this talk. I'm going to share my screen and you can actually see what I'm going to be talking about. So let me do that there. Someone can put in the chat if they can see my screen. It should be a nice big title slide and we can get going. Someone can type in the chat and I'll know that I'm not just talking into an empty camera. Works fine. Good stuff. Thank you very much, Kevin. So my name's Robin Moffatt. I work as a developer advocate at Confluent, who you may perhaps have heard of. We're one of the companies that contributes to the open source Apache Kafka project. And we've got our own distribution and cloud service and all sorts of good stuff like that. So I've been doing this kind of thing for a few years now. I've been working with Kafka for 4 or 5 years. My background's in data engineering, as it's called nowadays. I was just building data warehouses back in the day. And this evening, as it is over here in the UK and so Central European time, I want to talk all about what Apache Kafka is. But before we actually get into what it is, I want to lay the scene for why do we even need Kafka in the first place? Because as computer people, we like the tools and the kind of the cool little things like that. But I want to start off by thinking about well, why do we even need this thing? So I'm going to go through a bunch of stuff. If you have questions along the way, please put them into the chat. When I pause to draw a breath and get a sip of water, I'll have a look over. I'll do questions as we go through, or I might save it to the end if I think it's going to be a longer answer. So do put your questions into the chat and we can do those, as I say, as we go through or as well at the end. So the whole reason for why we need something like Apache Kafka is events. This little word, events. Because events are actually this really, really important thing that we don't actually spend enough time thinking about. I work with Kafka, so I spend quite a lot of time thinking about them. But in general, when we're working with data and we're thinking about how we're going to handle the data within our organization, we think about data and we think about rows and we think about databases or NoSQL stores. But most of the data that we work with started life as an event. Because an event is this concept. It tells us that something happened and it tells us what happened. And it happened at a point in time. So if we take this abstract concept and think about the data around us in our particular domains in which we work, events are actually everywhere. Because we have events that are generated by humans. We walk into a shop, or nowadays we click on a website and we buy something. So there's an event. Something happened. There was a purchase. What happened? Well, what did I purchase? I bought a can of baked beans. So there was an event, that something happened, there was a purchase. What happened? It was a tin of baked beans. This was the purchase price. This was the store in which I bought it. And it happened at a time. And we have things like stock movements and people moving inventory around warehouses. So there's a something happened, stock moved. What happened? Well, it moved from here to here, and this was the requisition number and all that kind of stuff. But these events, they're happening over time because life happens over time. So events model what's happening in the real world. Events aren't just human generated. Events can also be generated by machines, obviously at a much greater rate usually than humans do. So we have networking devices, for example. We have our routers with all the packets going through them and our switches, and they can tell us this particular packet was on its way to this particular port from this IP address, and those are events. We have IoT devices saying, at this particular point, the temperature was this, or this door just opened, or this camera just took a picture, and those are events that are happening over time. Our applications are also a source of events. The user did something. The application fell over and threw a stack trace. Those are also events. So whether we're thinking about modeling within our business, the process by which something is purchased or stock is moved around or a trade is placed, or whether we're thinking about the systems on which we want to drive particular actions or analyze what's going on and what's our network traffic doing, or is there a security threat here, or these devices that we've got around the edge, they're kind of telling us to do this thing. Events are really, really powerful because events are everywhere and they model the real world. And they're super powerful because they let us do things. The idea of an event-driven architecture. So by saying when something happens, we'll go and do something in response to it. When an order gets placed, we'll run a fraud check. This idea of breaking things out into services, and a service is responsible for something. So when someone moves some inventory, this service over here will go and update something or go and check for that. But events aren't just about driving actions. And this is why Kafka is so important. I'll explain why it particularly is in a moment. But just bear in mind that events are used for driving things, But events are also the source of the data which we build all of our analytics around. So all of those systems which are building dashboards against databases, all of that data started life as an event. So by capturing an event when it happens, that order is going to be useful downstream for building out analytics and how many cans of baked beans did we sell last week. That order is also going to be useful for telling us, like, this service over here needs to go and do a fraud check, and this one over here needs to go and do a shipping notification. But it's the same events that happened. So we want a way of capturing these events and modeling what's going on in the world around us so we can actually build really cool systems on top of them. And these systems are going to be event-driven, and they're going to be near real-time, and they're going to be responsive, and we're going to have accurate data to work with. But let's start boiling it down into, like, how we're going to build this thing. Conceptually, we have an event. This humble little rectangle here is an event. Now, events don't happen in isolation. We have lots of events. Now, events could be happening at a rate of a gazillion a second. If you're like Twitter and Netflix and Uber, like, you're talking about like big data, and things happen super fast, and it's like, who's got the most million events per second that they can kind of talk about, and that's great, and that's super powerful and exciting. But events happen over time, and we're going to talk about how we capture them in a moment. But there's nothing that says they have to be occurring at a certain rate for an event-based system to make sense. Because actually events could be happening at a very modest rate, like a few hundred per hour or whatever. The point is we're going to model these events in their native state, because we're going to say an event is basically, well, let's, for now, we're just going to call it a key and a value. We're not going to get any more complicated than that. And like, obviously within an event, there's stuff that happened and there's data we want to capture and kind of encode and all the rest of that. But we're not going to kind of get ahead of ourselves here. We're just going to say, for now, an event, it's got a key and it's got a value. We'll talk later on about how we actually make sure we can store data in a state that's readable within that. So where do we capture these events? These little key value events that are happening continuously over time. So we get to the first concept of Apache Kafka. Apache Kafka is a distributed, immutable commit log, which sounds fancy. So let's for now just say a Kafka is a log. So a log is this very, very special concept. And if what you hear this evening is interesting, go and read a book. There's an article by Jay Krebs, What Every Software Engineer Should Know About the Log, I think it's called. And there's a book related called I Heart Logs. I heart, little emoji, heart logs. And the log, like maybe you're thinking of like my application, it writes a log file, and that's type of a log. But the log we're talking about here is a very, very special thing, because a log captures events. So I click on a website. Clicks are also a good example of events. So I click on something, that's an event. So Robin came along and he clicked on the login button on the website. So that's an event, we capture that onto the log. And then he clicked on here and he clicked on my orders, and then he clicked on here and he went to edit an order, and then he clicked on here. And all of these events we're capturing onto this log. And what we're doing is capturing, it's appending it onto the log. Each time something happens, we append that event. Now, there are a few really, really powerful guarantees that Kafka gives you. And the first one of these is that data is immutable. So when I click on that website, I can't unclick on it. So I click on login. I guess I could go and click on log out, but that's now two events. I've logged in and then I logged out. I can't undo that first login. So these things are immutable. It's like if you have a conversation with someone, perhaps you have an argument and it gets a little bit heated, you can't unsay those things that you've said. So once an event has happened, it has happened, and we capture it in this immutable fashion onto the log. We also make sure that we retain the order of those events. And there's a nuance to that, which I'll address in just a moment. So we have these immutable streams of events. We can't undo an event. We could counteract it by appending another event, which negates the first one. But we have these events that we're capturing. So what are we going to do with this log? Well, what we're going to say is within this log, it is immutable. It is append only. But capturing just one great big log of all of the different events within our business is going to get pretty big and unmanageable and unwieldy fairly quick. So we need a way of actually modeling those events into something which we can actually start to wrap our heads around from a programmer's point of view. And this is called topics. So we carve up the log conceptually into what are called topics. And topics, if you kind of like from a databasey background, they're kind of like tables. They're our entities, they're our data structures. So we've got a topic here at the top called clicks, and these are all of our clicks in this immutable append-only log. And we've got orders. Someone places an order and they place another order and the order gets updated or whatever. These are the events to do with the order entity, and it is append only and it is immutable. We've got a third one at the bottom of the screen there called customers. Now, clicks are a series of events, like clicks happen over time, orders, they happen over time, their status changes over time. Those are relatively straightforward concepts of an event stream to get your head around. Like, these things happen over time, you can't go back and change it, that's fine, that's an event, we're going to capture it into a log. But what about a customer? Like, I'm a customer, am I an event? Well, I'm not an event, I'm a thing, I have a particular state. But as I enter a system, I'm created, and then I change my address, and then I change my email address, and then this happens, and I change my marketing preferences, and all of those different things are events. And we capture those events onto this immutable log, and from those events, we can build up state. So we can say, okay, here's Robin, he created his customer profile, and then he changed it to this, and then he changed it to that, and you can take that and you can condense it into state, and you can say, okay, what's the current state of this user, Robin? So capturing what I call as black and white reference data onto a topic is completely valid, and it's a very good thing to do, because then you can start joining between these different things within the Kafka ecosystem. But I'm getting a little bit ahead of myself there. So we have the log, which you're going to cut up into topics as a way of arranging our data. Within the topics, we have this concept called partitions. So partitions is kind of like it's an implementation detail, and it gives us our unit of scalability. Because as we'll see in a moment, the way in which we read and write data comes down a lot to how we've arranged it in terms of partitions. So a topic has one partition as a minimum, and you can increase the number of partitions as you want to. So here's our next guarantee that we get. I touched on this earlier, but within a topic's partition, you have a strict ordering guarantee. So if you have a bunch of orders coming in, and depending on how you write to that topic, which I'll talk about in just a moment, those messages will guaranteed to stay in the particular order. So we wouldn't be able to say, oh, we're going to read the messages from this particular topic within a partition, and this order shift. And you say, well, what was the order? We've not created it yet. You're guaranteed that if you say there was a create, and then there was a fraud check, and then there was an invoice, and then there was a ship, when you read those events back from a particular partition, you're guaranteed that they will remain in that order. So that's a really, really important thing. So we now need a way to get that data in and out, because Apache Kafka, it gives us these pub sub characteristics, which you may be familiar with from other systems. So let's think about the pub side of things to start with, the publish idea of getting data onto a particular Kafka topic. So when we produce data onto a topic, it's relatively straightforward. What we're going to do is we're going to say, I have an event or a set of events. I would like to append those to the end of the topic. You can't say, I've got this event here, I'd like to go and change that one previously, because if we remember, the log is immutable. We can't go and say, well, that one that I wrote before was by mistake, whatever. You can't do that, it's immutable. All we can say is some new events have happened, we'd like to append those to the log. So the producer API within Apache Kafka is responsible for doing that. It takes the data and it sends it to the broker. I'll talk about what a broker is in a moment, and it writes that into our Kafka topics. So you have various different libraries for different languages. So here's an example of what it looks like using the producer API in Java. There is Go, there is C++, there is .NET, there's Python. Whichever language you're using, there's going to be a client library for it. And it's relatively straightforward. It says, where is my broker? What is my payload? And we send it off there. So the broker is responsible for actually receiving those messages and writing them to the topic. Now, I talked about partitions and I talked about ordering of data. So this is one of those things that when you get into using Kafka, you actually need to apply some design thought to. If you've just got a bunch of data, you don't care about the order, you just want to make sure that it goes into a particular topic and you really don't care which partition it's going to go into, you don't have to set a key on your events that you're sending at all. You just set the value. So with no key set on those messages that you're sending, they just get spread out across the partitions, and eventually they end up like nicely balanced out. So this changed in Kafka 2.4, I believe. It used to be like a round robin assignment. Now it's to do with batching and stuff like that. But it ends up like eventually nicely balanced out across those partitions. But if you think about orders, for example, I keep coming back to this canonical example of orders, you want to make sure that when you're reading that order data from a particular partition, that you have all of the orders for a given, all of the events for a given order within the same partition. Because as we'll see in a moment, when you read data out of a topic, you can actually have separate applications doing it, and one instance may actually only get data from a particular partition. So you're going to want to make sure that that particular instance gets all of the events for a given instance of an entity. So in that case, you say we're going to make sure that we set the key of the event so that all of the instances of that particular entity will end up in the same partition. Now, if you've got 10,000 orders on your system, it doesn't mean you need 10,000 partitions. You could have 2 partitions. Each partition will get 5,000 orders. But the point is, within those 5,000, any events for a given order are guaranteed to be in that partition, and they're guaranteed to be in strict order as well. So that's about all there is to producing data onto a topic in Kafka. So we have the client application. It wants to send data onto a topic. It puts the messages onto the topics. You just give it the broker. You tell it where the Kafka brokers are. It handles the partitioning stuff. We decide as application designers, do we need to set a key for it or not? And off we go. There's various different client libraries. There's even a REST proxy that you can use as well if you'd like to. So, relatively straightforward getting the data in. Getting the data out is a little bit more considered. There's a few more nuances to it to think about. Now, when we come to read data out of Kafka, we have a sequential access. So you can go to any point in that topic that you have and say, I would like to read data from this point. And then you scan forward with your application. So we could say, we've got a particular application, Sally's the application over here, connects to Kafka, says, I would like data from this particular point onwards. That could be a given offset within the log. So within log, it's broken up into offsets. And you say, well, from offset 43, give me all of those messages from there onwards. It could also be based on timestamp. So Sally could come along and say, I would like all of the messages as of midday yesterday. And Kafka says, OK, well, that translates to this particular offset. And here are all of those messages from that point onwards. Now, what sets Kafka apart from other systems that you may be thinking of in this kind of genre of like, I've got data, I put it in, I read it out, it does pub sub. Kafka differs hugely in that you can have multiple consumers of that data, and those consumers are independent, completely independent. And when consumers read data, it's not deleted. So Sally's happily reading data from that particular point onwards. Fred comes along, Fred's our fraud checking application or something, and says, well, I've not read any of this data yet, so I'm going to go back to the beginning of the topic, and I'm going to scan through. Now, it doesn't matter if Fred is kind of like running on a small little one-core server and it's like chugging through those messages one at a time, or if it's like on some like souped-up EC2 instance that costs a lot of money to run, and it's like whizzing through them. The rate at which he's consuming it relative to the previous application, it's irrelevant. You just have 2 consumers independently reading the messages from the topic. So these 2 consumers might be the ones that we had in mind when we started populating that topic. So we said we're going to capture order data, we're going to write it to a topic, we've got a fraud check application, we've got an invoicing application. They'll do their separate things, nicely loosely coupled, and they'll just read those orders. But then someone else comes along and says, well, actually, we've got order data, that's great, we can use that to build our data warehouse tables, because we can read that data that you've got, that transactional data. I'm going to go stream it into an analytics platform over here. And so then they come along and they can read that data also. So you can add in additional consumers as you need to. The data is only deleted from the topic when we tell Kafka that we want to get rid of data from that topic. So we say, this particular topic here, we're going to set the retention based on size. So like keep 10 terabytes worth of data, or time, keep 7 days worth of data, or indeed you can have infinite retention also. So orders, perhaps we say, well, we want 10 years worth of orders, or customer data, we're actually going to keep all of that forever. There's something called topic compaction, where it retains the latest value for every key. That's worth bearing in mind if this the kind of use case you're thinking of, and that's another variation of keeping the data forever also. So again, lots of different client libraries. Consumers connect to the broker. They say, here is the topic I would like to read data from, and they poll for the messages and they process those and they get a key value back. So if we think about a topic here, we've got 3 partitions within it. We've got a single application. So maybe this is our application, Sally, that's doing the invoicing. and reads those messages from a topic. So single application instance reads data from all 3 partitions. We may say, well, actually, we've got 2 consumers. So as we had in that previous slide, we've got one application over here that's reading the data, one application over here that's reading the data. If we have a single instance of each application gets all of the data from all partitions. So that's all those different lines squiggling across the screen mean. If you line them all up, A1 application 1 gets data from all 4 partitions. A2 gets all data from all 4 partitions. Because they're separate applications, they need all of the data from the topic. What happens though, if A1, our application up here, maybe it's the fraud checking application, it can't keep up with the rate at which the messages are arriving on the topic, and it's supposed to be processing them. So it's got some kind of SLA, and we're supposed to kind of have processed all of the messages within like a second of them arriving, and the topic backlog is getting bigger and bigger and bigger, and we're like, we just can't process them on a single instance. Well, then we can scale out the consumers within a given logical application. So A1 here on the screen, instead of a single instance of it, we create additional instances of it. So we still have 2 applications, A1, A2. It's just that within A1, we've got multiple instances of it. So this is called a consumer group. So within a consumer group, so here's A1 zoomed in, and we've got 4 different consumers within that. Kafka will manage the allocation of the partitions. So in this case, we've got 4 partitions, 4 consumers within the consumer group. Each partition is allocated to 1 instance of that consumer. So this is where it comes back to the keys we use for our data, because if we have C1 over here, it's reading all of the data from this particular partition, it's going to need to know about the order. In a particular instance, it may need to know about the orders in that particular partition in the same instance of an order. So we need to make sure that they're going to end up in that same partition. It may be it doesn't matter, in which case you can pay less attention to it, but that's how it works if you're going to scale out your process in that way. Now, what happens if we say, well, actually, we don't need 4 processes? Maybe the throughput is like sufficient. We say we can make do with 3. Maybe one of them crashes. So we lose one of the consumers, whether deliberately or not. Kafka says, OK, we've got a partition down here, partition 4. It's not being consumed from anymore because the consumer's gone offline. So like Kafka keeps track of this. And it says, well, we need to make sure that data is being processed. So it says, OK, C3, you're up. You now get data from 2 partitions. And Kafka manages this balancing out of consumption of the partitions to make sure that within a consumer group, all of those partitions are being consumed. So consumer API, it's a little bit more complicated because of how it works and how it lets us scale our processing. And hopefully we can see from what we've, what we've talked through there is that if you only have a single partition, you can only have a single instance of a consumer. You can have multiple different consuming applications, but consumer group for an application can only have 1 consumer. The others are just going to sit there idle. So we scale out our processing by having multiple consumers, which therefore means we need multiple partitions. So if you say like my maths on the back of this napkin means we need 10 instances of our application, you need a minimum of 10 partitions to be able to drive that kind of throughput. You could have 20 partitions, and each instance within the consumer group will get 2 partitions and so on. But you've got to have those partitions there in the first place. And you can repartition your data if you kind of get it not quite right the first time around. But when you start repartitioning, you then need to be careful about the ordering of the data, which depending on your business case may or may not matter. So consumers, they're a client application, they read data from a topic, they're scalable horizontally, so long as it's a stateless application. If it's stateful, we'll talk about that later. And there's a bunch of different client libraries. Okay, where are we actually going to keep this data? We're going to keep it in a log, which is broken down into topics, which is broken down into partitions. But where does it actually live? Where's the box that I go and kick if things aren't working, or I go and put the CD in to install it, or nowadays just download a package off the cloud? Well, it lives on brokers. I've talked about brokers a few times, but what actually is a broker? A broker is the JVM process that runs Kafka. When we go and install Kafka, we're installing the binaries that we spin up, and it runs a JVM. Within it, it's a Kafka broker. Now, Kafka is a distributed system. I said earlier the words distributed immutable commit log, and it's distributed because we have multiple instances of a broker. You could have a single one. You could just like run a single instance of a broker, but that's not distributed, is it? That's just like a single instance of it, and it's fine for running on your laptop, but that's not where Kafka's real strengths lie. Kafka's strengths lie in this massively distributed, hugely performant, scalable system. So you can have your data distributed and spread out for performance and resilience across multiple different brokers. So multiple brokers form a cluster, and your partitioned data is spread out across those brokers. But as is common with distributed systems, we hold replicas, we hold copies of that data. So partition 1 is spread out across other brokers. Partition 2, partition 3, partition 4 are also spread out across the other brokers. How much you have in terms of replicas is configurable. So you could say, well, in this case here, we've just got like 2 replicas and the original. You could say this particular topic here, actually for storage reasons, we're just going to have a single replica, single instance of it, which means you've got no resilience whatsoever. You can have another one which says, well, this one here, it's like super duper important. We would need like belts and braces and all of the rest of it. We're going to have like 7 replicas. Obviously, you need 7 brokers at least then. And what Kafka will do is it will say, well, if you lose one of those brokers, then one of the other machines will take over as the leader of that partition. So in this case, we lost broker 3. Partition 3 was over on broker 3. Like the numbers are kind of like, they line up conveniently, but that's not actually how it would work. But in this case here, we've lost broker 3. So broker 2, which had a follower partition, a replica of the third partition, that takes over as the leader of it. So this is kind of pretty good. We've got a distributed, highly scalable performance system that lets us capture events as they happen, that lets us subscribe to those topics and read those events as they're happening. We can build systems that are event-driven, that are loosely coupled. We can drive our analytics. This is pretty cool stuff. But actually, this is just the core of the Apache Kafka ecosystem, because we're not really finished. In fact, we're only just getting started. Because if you think about the kind of things, and hopefully you've been sat here enthralled in what I'm describing, hopefully your mind started wearing, think, well, I could use it for doing this, I could use it for doing that. And different ideas might spring to mind. You might think, well, I could build myself something around Kafka and say, well, I've got this database over here. And I saw this talk at JCon once, and this guy was talking about the producer API, and I could write myself some Java, and I could pull the database, and every time something changes on the database, I could write it to a topic. And then I've got a mate on the team over there who's pretty good at Python, and then we use the Python consumer API, and they're going to push that into S3. And we can build out this streaming pipeline. So anything that happens in the database, we could go and push into S3. And Kafka will act as this buffer and kind of apply back pressure, and it'll be resilient and scalable. And in fact, we can reuse that data. And my friend in that team over there, she's really good at .NET and is going to write something to go and stream that data into HDFS. And this is really good. You think, well, I can write all of these different things using the producer and consumer API. Or we say, well, actually, we've got a new application that we want to write. And our new application over here, we want it to be event-driven. But the events at the moment are going to be kind of coming from an existing application over here. And that existing application is built on top of a database. How are we going to do that? We say, aha. Well, maybe we go to the database and we say, well, actually, within a database, it's made up of state, but when the state changes, that's an event. So we could capture the events out of the database into a Kafka topic and drive our new application, our event-driven application from there. And this sounds brilliant. And we could write ourselves a framework, in fact, because as well as our friends and colleagues who are going to build a streaming pipeline, we could write something similar and we could make it like a framework and scalable so that when we pull the database and capture these changes, and this is great. And we're going to go to management and we're going to say, we need 6 months to build out this framework for doing integration between Kafka and other systems. Now, as Admiral Akbar would tell us, it is actually a trap. It's a very kind of like enticing, well-meaning trap, but it's a trap nonetheless, because someone spoiled your fun. Already we have an integration API for Apache Kafka, and it's called Kafka Connect. So what Kafka Connect does is it provides this framework for pluggable connectors to stream data in from numerous sources into Kafka and push that data down to numerous different targets. So we can build ourselves streaming pipelines, like taking data from this analytical database here and pushing it to that cloud data warehouse over there, or reading that flat file or message queue here and putting it into a NoSQL store and wherever else over there. And we don't actually need to lift a finger to write a line of code. It's just configuration. I mean, there is an API, and if there's a connector that doesn't exist yet, we can go and write it, but there are hundreds of these connectors already. So we can hook into databases and message queues and cloud data stores and node SQL stores and anywhere else you want to. It's a pluggable architecture. You have connectors, you have transformations you can apply to the data also, and it also handles serialization for us, of which we'll speak more in a moment. So Kafka Connect runs separate from your brokers. So if your Kafka brokers, your JVMs that are sat there running away doing the brokering, you have Kafka Connect workers, which run separately and are also distributed and scalable and fault tolerant and all that kind of good stuff. You can get the connectors from Confluent Hub. So you can type in the connector name and various different ones from the community, from vendors, from wherever else you can get off there and download. You can install it yourself, or there's a tool that will do it for you. So I said about serialization a moment ago, and I said at the beginning of this, we've got these boxes and we're going to call them events. And for now, let's just talk about keys and values. But actually within those key value bytes, which is what we put onto a Kafka topic, it's just bytes. What actually is it? Well, one thing which I hope it isn't is this, because heaven knows what that's supposed to be. And it's a payload, it's a value, we can write it onto a Kafka topic, because Kafka doesn't judge. I'll probably judge because schemas are kind of like important, we need to do it right. Kafka doesn't. Kafka just says, give me some bytes. And it says, I'll store those bytes, key bytes, value bytes, write them as an event onto a topic. But as application designers, as software engineers, we need to think about what those bytes actually are. And we need to think about how we're going to serialize them. And this is where schemas come in, because we've got our serialization methods, and with those, we've got choices around how we're going to manage the schema in the data. And if you're sat there thinking, schema stream is like, yeah, I'll worry about that another time. Schemas are actually really, really important. And if you don't quite realize that yet, you probably will later on. It's really worth bearing in mind, because schemas act as the contract between these services that we're building. They're like the APIs. So if we're using Kafka to build ourselves a nicely scalable, loosely coupled set of services, those schemas are the contracts that glue those things and enable them to work in a nicely, loosely coupled way. If we start interchanging payloads that look like this, the first thing that's going to happen when someone wants to read that data, they're going to phone you up and introduce a coupling and say, what on earth is this? And is it tab separated or space separated? Or is there like a funny little control character? And is that first field a date, or is it a key? Or like, what on earth is this? There are much better ways to serialize data. You've got things like Avro, you've got Protobuf, you've got JSON schema, all of which declare explicitly a schema, and they store that schema in a schema registry. You can use JSON, but it doesn't actually enforce an explicit schema. You're kind of eyeballing it and guessing at it. If you're using a schema registry can actually enforce compatibility guarantees. It can say, when you write a message onto this topic, it must be compatible with a schema that's been declared for that topic, which means that breaking pipelines just happens less and less often, because even if you meant to, even if you're just being lazy, or like, let's just force it home and worry about that later, you can't. So you can't make changes which are going to break your consumers. So I'm hopefully not even going to use CSV. We can talk about that offline if you actually think that would be a good idea. So we have our producer. It sends a message onto the topic. It writes the message, the schema of that message into the schema registry. And then our consumer or consumers, multiple ones, they can read the schema from the schema registry. They can deserialize the message and apply it to it. So that's schemas. They are super important. So think about schemas, think about your serialization methods. I want to kind of progress towards the end of this. We're nearly wrapping up. I'll summarize where we've got to and do a few questions. I can see they're coming in, which is great. Keep them coming. But I want to finish off by thinking about what's actually going on here when we start reading data from a topic. Because we've talked about PubSub. We've talked about something happens in the business. We're going to capture it as an event. We're going to produce it onto a topic. If it actually happens in the business in another system, we're going to really hook into it using Kafka Connect and stream that data in directly. If we want to push that data from a topic out to another system, again, Kafka Connect fits the bill. But there are plenty of things that we want to build reading data from a topic that we're going to write some consumers for. So here's consumer A, it's a consumer group, it's a particular application that's doing something. But what are the things that we actually do with a stream of data? There's a kind of a finite set of patterns. It's a very long list, but there are some key things that it would end up doing when it comes to working with streams of data. So if we think about like kind of a manufacturing plant, and we've instrumented all of the machines, and this is the kind of payload that's sitting on the topic, and we kind of crack our knuckles and roll up our sleeves and say, right, we're going to write some stream processing against this. We're going to read our streams of data. This is really interesting. We're going to say, well, probably want to take this data and we want to build an alert. And whether we're talking about manufacturing data or order data or network data, alerting on something having happened is a common requirement. We want to chart it. We want to say, well, group by this and like how many of these things happened in this particular time period. Or getting a bit more complicated, like, well, within this time period, did this thing happen here? And maybe join out to that thing over there. Or in fact, maybe let's just take this data and go and push it somewhere else, and we can use that to drive analytics. But these are some of the things that you end up doing using stream processing. But basically, we're saying within a stream of events, we want to do something to it. So let's take the first example. We want to filter it. So we have a stream of widgets, and then red widgets and yellow widgets, and they happen over time. Remember, we're talking about an immutable stream of events. So these are happening. Maybe it's 1 million a second, maybe it's 100 an hour, doesn't matter. It's a stream of events. And we say, well, within that stream of widgets, we would like another stream of widgets just for widgets which are red. So over time, these widgets come in and some are red, some are yellow. If they're red, we'd like that on this separate stream, because that stream there, it's going to be used to drive a service over there, which says, when a red widget happens, when a red widget is made, I'm going to go and do something. I'm going to go and do a push notification and say, yay, we made a red widget, or something like that. But we want to drive a particular service based on a filter we're going to apply to a stream of events. Well, Apache Kafka gives us that ability. It ships with something called Kafka Streams. And Kafka Streams is a Java library that you can use to do stream processing against your data. You can filter your data. You can say, here is the stream here. I would like to filter it out into a new stream. So read from this Kafka topic and write to that Kafka topic. As something happens here, process it, filter it, write it there. And you can do filtering, you can do joining, you can do stateful aggregations. And stateful aggregations is what I was talking about earlier when we talked about the scalability of a consumer. And if it's stateless, you just have the consumer API and you spin up additional instances. If you have stateful processing, this is where Kafka Streams comes in. You can build tables on top of the data, and it uses Kafka in the background to maintain state, and it can scale out and do all sorts of clever stuff like that. So Kafka Streams gives you that ability to do stream processing within the Kafka ecosystem. Something from Confluent is called ksqlDB. It's community licensed, and it's actually built on top of Kafka Streams, and it gives you a SQL interface to doing stream processing. So I showed you the previous example where we said we're going to use Kafka Streams, and here is our bit of Java code that's going to filter this into that. Well, the equivalent in ksqlDB is actually that SQL statement there. Go and create a new topic populated by the results of this select statement. So then when it comes to doing some of these things that we do with stream processing, we can say, well, we're going to do some filtering. So take this here and filter it for this condition. Or take this thing here and group it up by that to create an aggregate, or indeed create an aggregate and then apply a predicate also. ksqlDB also integrates with Kafka Connect. So you could say, well, just take this stream of widget data and go write it to S3 or BigQuery or Redshift or wherever you want to put your data today. So you may wonder, well, ksqlDB or Kafka Streams, which is which, or which one to use rather. It depends on what you're doing. So you think about, well, what am I actually trying to do? What's my skill set of my developers? Are they SQL writers? Are they Java coders? Are we doing something super low level? Are we doing something relatively straightforward, which is actually going to benefit from less boilerplate and just like running a SQL command? So each one has got its particular place in the ecosystem. So we've come, unfortunately, to the end of our time together. I'll wrap up and then we can do some questions. But we started off by talking about this humble event. Events modeling the world around us, a stream of events. Events are happening all of the time, and events describe things happening. They describe what happened and that something happened. So we have an order being placed. We have a network device receiving a packet. These are all events. And we said within Kafka, when you store it simply as a key and a value. It's just bytes, a key and a value. These are stored, appended to the end of a log, and it is immutable. So we have this data, it goes onto the log, and once it's there, it cannot be changed. You can't go back and make a change to a particular event. Around the log, we build some APIs. So we say we need a producer and a consumer API. These are low-level APIs for getting the data onto a topic and reading data from the topic. But then we say, well, actually, there's a lot of repeatable patterns when it comes to getting data in and out of Kafka. There's integration with other systems. So we say, well, we're going to add on to it connectors with the connector, the Kafka Connect API. We also said, when it comes to getting data out of a topic, sometimes we end up doing this set of patterns, which we can refer to as stream processing, and that's where Kafka Streams comes in also. So this is what makes up Apache Kafka. So Apache Kafka, it's an Apache Software Foundation project. It's made up of the producer-consumer APIs, the log, Kafka Connect, and Kafka Streams. Around that, Confluent has built a bunch of other pieces. So you've got that security, you've got the schema registry, which is community licensed, the ksqlDB, which is community licensed. And around that, we've also got Confluent Cloud. So if you want to go and try that out, there's a bunch of codes and stuff like that. So you can sign up to that and try those out. And if you want to learn more about Apache Kafka, there's a bunch of free material on Confluent Developer. So we launched this just a month or so ago, and it's got a bunch of like really deep dive stuff on there. So if you want to know more about Kafka's internals, if you want to know about like Kafka without Zookeeper, which is something you may have heard of, if you want to learn more about Kafka Connect, all these sorts of different things, that's all there free for the taking on Confluent Developer. There's not a paywall, there's not a kind of a gate or anything like that to access any of this material. So hopefully that's been useful for you. I'll take some questions. If you want to follow me on Twitter, I'm @Moff. If I don't get to your question this evening, please do send me a message on Twitter. You'll find me on LinkedIn. You'll find my email address out there as well. I'm kind of various places on social media. But thank you very much for your time. I do hope it's been useful. And let's have a look at some of these questions. If you do have questions, put them in the chat. I'll try and get to them. So we have a question from Sasha. Says, when I tried around with Vertex, I could configure Kafka in between the event stream by configuration. Does someone know something comparable for Spring Web Flux? I literally have no idea what half of that means. I'm really sorry. That's completely outside of my zone of knowledge. But let me put a link into the chat now of a really good place to go and ask that question. So let's send this to everyone in the meeting. So Confluent forum, there's lots and lots of chat on there about Apache Kafka, about Confluent platform. You'll find quite a few of the Apache Kafka committers on there also. Folk who use Spring and all that kind of stuff. So that's a good place to go and ask that question. Let's see if I've got any better luck with the next one. Is there some tool that could help to follow a message through a pipeline? For example, when one tries to debug some broken messages that is pushed down the pipeline and results in other messages. So one thing that springs to mind are headers. So Kafka Messages, I kind of skated over this. In fact, I didn't mention it at all. Kafka Messages, they're not just a key and a value. There's also, it's got a timestamp and it's also got headers. And headers, you can put kind of what you want into there. So depending on how you built your pipeline and with what tool and tooling and so on, that would be one option. Another thing to go and look at is this business around distributed tracing and what's it called, open telemetry. I can't remember what the various projects are called. But if you send me a message on Twitter or LinkedIn, I can dig out some links or go and look up kind of distributed tracing in Kafka. There's some useful stuff around that. That may also be useful. Question, is the ordering not guaranteed when we repartition or when we scale up the consumer group? How do we ensure strict ordering in those scenarios? Okay, so ordering is not guaranteed when you repartition, depending on how you do it. And it depends on the logic that you want to apply to those partitions. So perhaps you write yourself a Kafka Streams application, which reads data from your first topic, which has got fewer partitions, and writes it out to a new one, and it can enforce that ordering logic, and like how it does it. But if you just say like increase the number of partitions, then that's the ordering is not going to be guaranteed to be kept. If you scale up the consumer group, then this is where the stateful stateless thing comes in, because if it's stateless, then it doesn't matter if a particular instance within that group starts reading from other partitions. So that bit shouldn't matter around the ordering if it's stateless. So that I think that's the right answer. But again, go and check on the forum. There's a Kafka Streams category. Matthias Sachs is one of the committers. He's super awesome and really active in the community. He will set you straight on that if I've not answered it entirely correctly. How do we handle poison pills? Do we have something like dead letter? So in Kafka Connect, you have the dead letter queue for a sync connector. So connectors can opt to send a message to a dead letter queue. There is an article on the Confluent blog. Let me see if I've got it on my clipboard. Error handling. No, I don't. But again, send me a message on Twitter and I'll dig out the link. All about error handling in Kafka Connect and dead letter queues. I think within Kafka Streams, there was a friend in the community who wrote an article around that. But again, send me a message. I can follow up specifically the area that you're interested in there. What are a common number of partitions, asks Sven? Is it better for a future scalability or does it come with a cost? So this is a really interesting one. There's an article, I think, on the Confluent blog which addresses this. If you have too many, then things slow down, which is one of the reasons why Zookeeper is being removed from Apache Kafka. So Apache Kafka 3.0 was released a couple of weeks ago, and that, again, progresses this move away from Zookeeper. It's still needed for production, but there's like early release candidates there if you want to try it without it. And that moving the metadata about partitions into Kafka itself is going to help massively around how many partitions. But in general, I think there's a rule of thumb around, I think it's 12. But again, ask on the forum or on Twitter, and people tell you kind of the actual guidelines to follow. But I think starting off with more than one, but less than like 1 million is probably a good idea so that you don't end up repartitioning down the line. But again, that's a really good one. So if you do the Twitters, please send me a message and I'll retweet it and we can get a consensus from the community what the latest thinking is on that. Oh, awesome. Jens says there's open telemetry support for Kafka. That's awesome. Thank you. What's the main difference to a messaging system when I use a pub sub topic? I don't fully understand the context of that question, but I think, in short, Kafka stores data, which a messaging system generally is transient. So I'm kind of like, I'm generalizing massively because I'm not sure which messaging systems you've got in mind. But Kafka stores data. So Kafka's not just this transient, like messages come in, messages go out. When one consumer's read it, or we declare ahead of time there are going to be 10 subscribers, and when they've all read it, we can delete the message. Kafka doesn't work like that, which makes it much more scalable. And also architecturally, you kind of like rethink how you actually see it within your architecture, because you think of capturing the original event, and that's going to be useful in a transient sense for like these services have read it and then they never read it again, but also services that may want to reread that data. And we may have machine learning models that want to read that data and like try out a particular thing and then reread that data again. We might want to use that data to go and populate a cache and rebuild that cache if we need to. So the fact that it's not transient is a massive thing. The fact that it's much more scalable than lots of other systems is another thing as well. But if you've got more details around that question, please do ask. Does a topic have limits? Can it grow to infinity? So there's another comment there saying it can grow as far as the underlying database grows. So this may just be a kind of like a terminology thing, but Kafka doesn't have a database. Kafka writes topics as log files or segment files on disk, and there's no database. So like your Kafka architecture is like your Kafka Brokers and Zookeeper currently, but that will be going at some point, and it actually stores the data on disk. But conceptually, that answer is correct, as in, excuse me, if you have a broker that has got 2 terabytes SSD attached to it, then your topics partition can only grow that big. So again, this is another thing around partitioning, because if you want to store 10 terabytes within your topic, within a particular topic, you either have one partition and some very big disks on a single broker, or all of the brokers to which it's going to be replicated, or you split that topic up into partitions. But basically, the physical storage is going to be one of your limiting factors. But there is something called tiered storage, which is being added into Apache Kafka. It's there in Confluent platform already, which lets you have this idea of offloading data from a topic onto something like S3, so that your topic, in effect, has infinite storage. It's just that some of it's going to be local, some of it's going to be elsewhere. Advantages and disadvantages of Kafka Streams versus pub submodel, and in which cases to use it. So again, I'm not 100% sure what you're asking there. I'm going to answer that as I understand it, which is what's the advantage of using Kafka Streams instead of the producer-consumer APIs. And if that's not right, then feel free to put in the chat a clarification. But Kafka Streams just abstracts a lot of the repetitive stuff that you're going to be doing with the producer and consumer. So things like building out state. So as we read through a topic like orders, we can work out what's the current state of the order. So like it was placed, and then it was invoiced, and then it was shipped. So the current state is shipped. You can build up that state within a stream processing application. And you can say, well, I'd like to join that to our customer data, which we're going to read from another topic. And you can do those joins within Kafka Streams. And it gives you those abstractions to be able to do that. You could program it yourself within the producer and consumer APIs, but you're doing everything bespoke. So it's a library there that enables you to do this stream processing. It would be extremely difficult and complicated to try and do just on your own using those producer and consumer APIs, at the lowest level. How would a restarting consumer avoid processing the whole event stream to get back to the current state? That is an excellent question. And that points out that I didn't explain fully how the concept of offsets work. So we talked about Kafka topics, and they have offsets, and a consumer can come along and say, I would like to get the data from this particular offset. But what I forgot to say is that Kafka keeps track of those offsets. So the first time a consumer comes along to Kafka, it's going to say, I would like the data from the beginning of the topic or from the end of the topic, so just new messages as they arrive, or any arbitrary point in between. But from that point onwards, Kafka says, aha, your application XYZ, last time you got to offset 63, which means that when you start asking for new records, unless you tell me otherwise, you're going to get records from that point there. And within your consumer application, you agree when you're going to commit and say to Kafka, yep, I've processed those. You can kind of like consider those as being read for my particular instance of the application. So that's how you avoid reprocessing. And that's the end of the question stream. And that's also at 10 minutes to the hour, which I believe is my time limit. So thank you, everyone, for attending the talk. Thank you for the excellent questions. If I didn't answer your question, if my answer didn't make sense, or if I answered the wrong question, you can find me on Twitter, you can find me on LinkedIn, you can find me on the Confluent forum and all of the good places where developer advocates tend to hang out. So have a great evening, everyone, and thank you very much.
Yes, thank you, Robin. This was a really nice wrap for this conference part of JCon. Thank you for this really great session and the great interaction. On behalf of the whole JCon team and our sponsors, I would like to thank you for joining JCon today. A big thank you to everybody who made JCon happen. Tomorrow, we still have 10 workshops. So this is just the conference part that is over for this year. Make sure to find out if there's a workshop that interests you or that you like to sign up to. You can do this via the session planner. And also, I'd like to take a moment to ask you all for feedback for individual sessions. You could go to the session planner, find the session you attended, and give feedback to the speakers. They would highly appreciate it if you would leave a smiley face with your feeling about the session and maybe some text to give them some context why you put a smiley or frowning face. And also for us as the whole conference organizers, we would love to have your feedback on how did you like the conference, what was good, what is something that we can improve on so we can have an even better JCon next year, hopefully with all of you. So thank you for today. Thank you for joining JCon, and I hope we can see us next year. Maybe in person, maybe online, who knows? But I wish that we see each other again. Thank you, everyone.